Welcome back to Lesson 6. Today we're diving into the weak nuclear force, the particle architect that allows the sun to shine. It's called weak because its range is incredibly short, less than the diameter of a proton, but without it, the universe would be dark. The weak force is mediated by three heavyweights, the W+, W-, and Z bosons. And when I say heavy, I mean it. A W boson has a mass of about 80 GeV per c², nearly 100 times heavier than a proton. This high mass is why the force is so short-ranged. But its real magic is flavor change. The weak force is the only interaction that can turn one type of quark into another. In beta decay, a down quark turns into an up quark by emitting a W- boson. This turns a neutron into a proton, changing the element itself. This alchemy is the sun's secret. To fuel nuclear fusion, two protons must fuse, but they first need to turn one proton into a neutron. The weak force mediates this transformation. It's a slow process, a bottleneck, which is why our sun has burned steadily for billions of years. While the W bosons carry charge, the Z boson is neutral. It's like a heavy photon, mediating interactions where particles just bounce off each other. The discovery of these neutral currents in 1973 was a massive milestone, proving the electroweak theory that unified electromagnetism and the weak force. It wasn't until 1983 at CERN that these bosons were directly observed, confirming the math and earning Rubbia and van der Meer the Nobel Prize. To recap the stats, W bosons are at 80.4 GeV and the Z is at 91.2. Their range, a mere 10 to the minus 18 meters. Tiny, but essential. You even see the weak force in your kitchen. The natural decay of potassium-40 in bananas is driven by these very same bosons. In the extreme heat of the Big Bang, the weak force and electromagnetism were actually the same thing. They only split apart as the universe cooled. Without flavor change, we'd have no heavy elements, no complex chemistry, and certainly no life. The weak force is the ultimate facilitator. Neutrinos, our ghost particles from Lesson 3, only talk to the world through the weak force. That's why they can pass through light years of lead. Ever wonder why these bosons are so heavy while the photon is massless? It's all about their interaction with the Higgs field, but more on that in Lesson 8. In the grand table of the Standard Model, these three particles occupy the crucial role of force carriers for the second strongest interaction in the nucleus. So, they are heavy, they are short-ranged, and they allow particles to change their identity. That is the weak force in a nutshell. They regulate the speed of life in stars, giving the universe enough time for planets to form and civilizations to wonder about them. Mastering the W and Z bosons is key to understanding why our universe isn't just a soup of stagnant particles. Change is built into the laws of physics. If you can read these diagrams, you're seeing the blueprint of particle decay. Every line represents a journey governed by the weak interaction. In our next lesson, we'll look at the force that lights our world, photons and the masterpiece of quantum electrodynamics. We are more than halfway through our masterclass. Keep these pieces in mind as we build the final picture of the Standard Model. Science is about the courage to ask why things change. The W and Z bosons are the answer to that very question. See you in the next one. Thanks for watching James Physics 101. Don't forget to check out the full particle physics playlist to master every piece of the puzzle.